Hi, everyone. So welcome back to another lesson. So in this lesson, we'll look at more properties of the Laplace transform, right? And uh, how it's involved in solving any order differential equation, right? So let's get started. Jesus, let's get started. Okay, so there's some properties of Laplace transforms that I need to cover first. So here's the first one. If the Laplace transform of a function exists, right, for any s value bigger than alpha, then if we were to compute the Laplace transform of e to the at of f of t of s, it's equal to the capital F function of s minus a. So what this means is it's a shift, right? So you're going to do a shift of the Laplace transform of a units either to the left or to the right, okay? And it's valid for s values that are bigger than alpha plus a, right? Okay. The second property is computing the Laplace transform of higher order derivatives. So if we know that a function f of t and its derivatives, these are its derivatives, are continuous on any non-negative integer, okay? And we know that the nth derivative at t is a piecewise continuous function on t that's greater than or equal to 0. Then the Laplace transform of the nth derivative at s is equal to this quantity here. Okay. And I will show you in action um, uh, how this is applied, okay, in solving any order differential equation. Okay, so the whole goal is transforming a uh, nth order differential equation into in this case, an n degree polynomial in S, which is easier to solve, hopefully, right? The last property has to do with if capital F of S is defined to be the Laplace transform of little f of t, right? And we're assuming that little f of t is piecewise continuous, okay? So if we know that a Laplace transform of little f exists, okay, and is of an exponential order of alpha, then the Laplace transform of t to the n times little f of t is equal to -1 to the n power times the nth derivative of capital F with respect to s of s. Okay. So I'll show you an example on computing the derivatives of Laplace transforms. And most importantly, you want to make sure you have this. Oh, oh yeah. And these are the properties of Laplace transforms that should be. You should write these down because we're going to get into the next few videos on solving um, second or third order derivatives, and we're going to use these properties here, right? Okay. And just to point things out, the Laplace transform is a linear function, right? That's what these first two properties mean, right? Because the Laplace transform of f of t, by definition, was the integral of 0 to infinity of f of t times e to the negative st dt. Okay. So if we just, it's pretty easy to prove actually. So if we have two functions f and g, right, the Laplace transform of f plus g by definition, is equal to the integral from 0 to infinity of f plus g times e to the negative st dt. Okay, and this would equal to the integral from 0 to infinity of f of t times e to the negative st plus g of t times e to the negative st dt. Okay. And that, so shoot, I'll write this over here. So this equals to, well, the integral from 0 to infinity of f of t times e to the minus st dt plus 0 to infinity of g of t e to the minus st dt. Okay, and this equals to the Laplace transform of f plus the Laplace transform of g, and that is the result for part, Jesus Christ, the first property there. Okay, and the second property just essentially means you're multiplying that by a constant. Okay, so the Laplace transform of c times f of t, right? F of t times e to the minus st dt. C times the Laplace transform of f, right? So that's how you prove the second property, okay? This was the shifting function that refers to this theorem here. In the last in the next three properties have to do with derivatives of functions for f, and then the last property just deals with so the last property here, Jesus Christ. So the last property here um, refers to the if we know the Laplace transform of a function that exists, then the Laplace transform of t to the n times f of t is equal to -1 to the n times the partial of n with respect to s. The derivative of the Laplace transform of f of t with respect to s. And this refers to theorem 6 here. Okay. And then most importantly is the table. So it's a good idea to keep this in hand. It will be useful. There is plenty of Laplace transform tables online, but yeah, this is just a brief table that is found in the textbook. Yeah, there's plenty more you can search for your worthwhile. So yeah, make sure you have at least this table, okay? Because we're going to use that quite often in the next few videos. So let's go over some examples. So let's compute the Laplace transform of this function. Would you know how to do it? We'll pause the video and try to figure out how to compute the Laplace transform of this function. Otherwise, I'm going to work this out in 3, 2, 1. Okay, so the Laplace transform of this guy, 3t squared minus e to the 2t. Okay, we know that it's a linear function, so this equals to the Laplace transform of 3t squared minus the Laplace transform of e to the 2t. Okay. And then we can factor out constants. So this is equal to 3 times the Laplace transform of t squared, and then minus the Laplace transform of e to the 2t. Okay. And now just you can just look at the table. Okay. So we know that so we have t squared. It looks like this form here, right? So we have a t squared. So the Laplace transform of this guy, so it would be 2 factorial over s to the 2 plus 1 power, right? So this equals to 2 over s cubed. Okay, 2 over s cubed. All right. Okay. So yes. Right. Okay. Yeah, so it's 2 over s cubed. Okay. So if I go back to the next slide. So this first quantity here, so it's 3 times 2 over s cubed. Okay. 2 over s cubed minus the Laplace transform of e to the 2t. Now, so e to the 2t looks like this quantity here, right? And so the Laplace transform of e to the at is 1 over s minus a, okay, when s is greater than a. So what that means is e to the 2t, its Laplace transform corresponds to this function, 1 over s minus 2, okay? And then s is greater than 2, okay? So by going to the next slide, so that is 1 over s minus 2. Okay? 1 over s minus 2. And we know the domain of this function has to be bigger than 2. Okay? So all together, so this is 6 over s cubed minus 1 over s minus 2. Okay? So that is the Laplace transform of 3t squared minus e to the 2t. Okay. Let's see. Here is another example. Um, try to compute the Laplace transform of t times e to the 2t times cosine of 5t. Try to figure it out by pausing the video and thinking about how to approach to a solution. Because once again, I'm going to uh, show you the solution right about now. Perfect. Okay, so if you notice, okay, so we're going to refer back to this property in Laplace transforms here. Okay, so we're going to use this property here. So the Laplace transform of t to the n times f of t, this equals to minus 1 to the n times the nth derivative of f with respect to s of s. Okay. All right. So yeah, so that is the theorem that is in question here. So now, so we know the Laplace transform. So here's how we're gonna magically get to the solution. So we know the Laplace transform of e to the 2t times cosine of 5t, right? Do you know what that is? Well, if you go to our table, so we have this quantity, so e to the 2t cosine 5t. So it looks like this quantity here, right? So this would be the corresponding Laplace transform of e to the at cosine bt. So if s is greater than a, so in this case, we know that the a is 2 and the b is 5. So the Laplace transform here will correspond to s minus 2 over s minus 2 squared plus 5 squared. Okay? All right. And let me actually erase some of the stuff here. We don't need that anymore. Okay. So let me rewrite this. So e to the 2t cosine 5t. So yeah, hopefully you connected those dots there. Um, so what that means is the Laplace transform here is equal to s minus 2 divided by s minus 2 plus 25, right? S minus 2 squared here. Okay, so the Laplace transform of t times e to the 2t cosine 5t is equal to, so the t exponent here is, it's a 1. So what that is equal to by the theorem, it's just minus 1 times the derivative with respect to s of this function right here, s minus 2 over s minus 2 squared plus 25. Okay. All right. So, okay. So this equals to negative quotient rule time. Okay. So, low plus 25 times the high, which is 1, minus high times the low, which is the chain rule, s minus 2 times 1 over low squared squared. And here we go. Okay. Um, all right. And so we can that's a lot of work. I'm not going to simplify things, but yeah, but this would be the correct Laplace transform of t times e to the 2t times cosine of 5t. Okay. So pretty straightforward. And the last one, try to determine the Laplace transform of this function. Wow, this is interesting. Cosine of n times x times cosine of m times x. I should say t. Sorry. Okay, that's what I meant. It's not x's, it's t. Okay. So what we're going to do is we're going to use a trig identity that may not or may be familiar to you. And it's yeah, it's this one. So cosine of A times cosine B is equal to cosine of A minus B plus cosine of A plus B for 2. So it's using the average of the angles for the cosine function. And this is probably, you've probably seen this in pre-calculus. So yeah, so we're going to use this trig identity to figure out the Laplace transform of cosine n times t times cosine of m times t. Okay, so if n does not equal m, you can use this trig identity. Otherwise, you have to consider cases if n is odd or even. Okay, so um, now, so Laplace transform of cosine of n times t times cosine of m times t. So this equals to cosine of, in this case, nt minus mt plus cosine of n times t plus m times t over 2. And we're taking the Laplace transform of that function. And we know that the Laplace transform is linear, right? So you can express this quantity here as 1/2 times the Laplace transform of cosine of n minus m times t, okay, plus the Laplace transform of cosine of n plus m times t. Okay. Okay. So pretty sweet, right? M minus m and n plus m are constants. So if we go back to our table, this so this function right here and this quantity would be the corresponding the Laplace transform per cosine of bt, if b is a constant. So we have cosine. One of the quantities for cosine is cosine of n minus m times t. So the corresponding Laplace transform would be s over s squared plus n minus m squared. Okay. And then it will be the same thing for n plus m squared. It's going to be similar, right? But you only have n plus m as a factor, right? So it'll be n plus m squared. Okay. Pretty sweet, right? So if we go back to that example, so okay, so this would equal to 1/2 times, in this case, s over s squared plus n minus m squared plus s over s squared plus n plus m squared. Okay. And that is the Laplace transform. So I hope that made sense. Okay. And as we finish off this video here, there are some comprehension problems for you to work with. Just using the techniques on figuring out the Laplace transforms of functions by using those theorems and properties I listed out. And in the next video, we'll look at the inverse Laplace transform. Okay, we'll look at the inverse Laplace transform. Unlike the Laplace transform, it doesn't have a formula, right? We just use our knowledge from what we know from Laplace transforms of functions that we know how to compute, right? Or what's given out in the table to compute the inverse Laplace transform of a function. So with that in mind, I hope you enjoy this. Stay tuned for the next video, and I'll see you soon.